So now let's continue in 14.5. So this is 14.5 continue. This will be just 2 videos for this one, I believe. Yeah. Okay, so what does the gradient tell us basically? So this was, so you have some, there's actually like some surface up here doing whatever, right? So you got some surface, and then these are gradients. These guys are, you can draw down here. You could put it up on the surface and draw it if you wanted to. Both of them you could. I mean, just put it up there like that. What is, but it, I mean, the actual directional derivative and the actual gradient is, this gradient's a vector in the xy plane. when you look at the gradient of just f of xy, then you get some vector down here. But what does it tell us? So this theorem next tells us what that is. All right, so let's write this up. So let f of xy be differentiable. Okay, just standard hypothesis. The maximum value of the directional derivative, meaning like if you have all these different directions, like at a point, right? So all these different possibilities. What's the maximum value? So the maximum value is the magnitude of the gradient of f. Right? That's a value. It's a real number. And this is the cool thing too. Well, they're connected obviously. And it occurs when u is in the direction of the gradient. So really, that's what I want you to know, is that the gradient, in other words, so the real kind of punchline here, these are my standard colors for the darker background here. So the gradient, if I can spell it right, so the gradient del f, basically we say points in the direction of maximum increase. I'm not finished with that statement yet, am I? The maximum increase on the surface defined by z equal to f of xy. So, I mean, your f, of course, is creating a surface. F of xy is creating a surface, right? Maximum increase. So just check, take a paraboloid. Then the maximum increase is always going to be pointing basically perpendicular to the values. We can do that calculation if you want, but so the example I always give for this in a classroom at Chaffey is you're sitting in a classroom here. This is north, right? And then you have all of our mountains here behind us. Not that low, actually. Okay, so, and then I asked the question, and then of course we're at Chaffey, so we're always on this surface, right? So if f defines the whole surface, including our mountains in the background, what direction points in the maximum increase? Well, it's always, depending on what classroom you're in, pointing towards the mountains. Right, so the gradient, if you were to define the surface to be, it's a very poor representation of our surface here, but if you defined our this f of xy to be the surface of the ground surface, then the maximum increase is always up the hill, right? It's always pointing towards the mountains. Okay, so that's what the gradient does. So very important, powerful deal, actually. Okay, so let me go and draw a surface now. So on a surface, it's probably okay. Doesn't need to be so big. All right, so here's your x and your y and your z. And then we have our generic surface up here. Let me just try one more time before I give up. I know I'm picky. I can't help it. That's not very good, but we're going to have to just leave it. Okay, close enough. Okay, and then I do want to go back and make this dotted back here. I used too small of dots on that guy. Oh well. All right, so there's my surface. So basically the concept here is you pick some point down here. If that's my point, then what direction is pointing in maximum increase? Right, so you have all the different possibilities for your u, right, whatever that may be, and so that's your value of u. Probably put in way too many of those, otherwise it gets a little confusing. All right, so you have the different values of u. Well, u is just a vector in the xy plane, right? So the maximum one is going to be your gradient. So let's just suppose it's this one. So if you do the gradient of f, then you go up to the surface, then this in that direction is the maximum. So that might be the maximum or steepest. So you can think of it as the steepest deal. Okay, let's well, we're actually going to prove that. That's what it says. Let's prove it. You can prove it pretty, I wouldn't say easy, but it's not that bad. It's just using cosine. Okay, so this uses some past stuff we already know. All right, so let's put in a hypothesis. Let's let f of xy be differentiable on R2, the xy plane. Okay, then when you define the directional derivative, the direction of u of f of xy, we can say that's the gradient of f dot u. Now, do you remember when you have, we'll just do this up here because it's, why not? When you have u dot v, that's equal to magnitude u, magnitude v, cosine theta. Right? That's exactly, we can do that. So we have a dot product of two things. We can write it in this form. That's why we did it way back when for a number of reasons. So that's magnitude gradient of f, magnitude u, cosine theta. Okay, where theta is the angle between gradient of f, and u, right? That's what it means when you have that theta. Well, if that's the angle between it, so going back to this diagram here, I said that this one we're going to have, let's change that color. This one right here we're going to have is, let's just say that's the gradient right there, and then I drew the picture up there. Okay. So your u is the angle between those. So let's just pick this one to be theta over here. So this is my u. So there's my angle. So what value of theta makes that the greatest magnitude? So cosine theta, we know this. Okay, so we know that cosine is between. So this isn't really even a geometric argument. This is algebraic. Cosine theta's range is between -1 and 1. We know that cosine theta is always less than or equal to 1. So when is cosine theta maximum? When theta is 0, right? So cosine theta equals 1 if and only if theta is equal to 0, meaning there's no angle between them. It's the same direction. So that's your argument. It has to be the same direction. Okay, so let me finish my statement here. So basically, what we get then is that, where am I at? I'll just say, let's see, where theta is angle between gradient of f and u, and then say and really, I mean that quantity, and so this quantity here is maximum when theta is equal to 0, or let's just say same direction. Okay, well, otherwise, I mean, then this is a fraction, makes this smaller. So that's your argument. So that's basically it. Okay, hopefully that made sense to you. All right. So if you go the opposite direction, it's minimum. So let's just put that in there. So opposite direction, theta is 180 or pi. Then minimum. Okay. Let's see where we're at here. I have an example for you. Okay, here it is. Next example. Okay, so I think I'll need to do one more video for this one. Yeah, I probably will. Yeah, gotta do one more. Okay, because that's a proof. It takes longer. So let f of x, y equal x squared plus 1/4 y squared plus 2. So basically that's a paraboloid shifted up 2 units, but it's not symmetric, right? Well, it's symmetric, but it's squeezed somehow, right? Squeezed a little bit. All right, so then A, find the direction f increases most rapidly at 1, 2. And maximum rate. Okay, so that's just simple. So you could do that calculation. I'll just kind of, well, I'll have to write it up, but I mean, I could copy it, but it's pretty quick. So you do the gradient, 2x plus 1/2 y. And note this constant doesn't do anything, it's just moving it up. I mean, it's just this. Instead of down here, it's up here. And that's all it's doing, right? Okay, then you evaluate that at your point, and you get 2, 1. Okay, so that's the maximum increase, and then you do the magnitude of that, and you'll get √5. So that's pretty straightforward. Okay, well, let's just continue. What the heck? All right, so next theorem states if f is differentiable at x naught, y naught, and the gradient of f of x naught, y naught does not equal 0. Oops, not theta. I meant to do 0 vector. Then the gradient of f of x naught, y naught, so like picture that as a vector, is normal or perpendicular to the level curves or level curve through that point, through x naught, y naught. So it's you got to picture like contour lines, and let's just continue. All right, so you have these contour lines. Let me just show you let me pull this up because I drew it real nicely before. I don't think I can match it. Oops. What happened to there? Oh well.